Diogo,
Hello.
great to have you here. It's been a long time.
Yeah, it's been a long time indeed.
How are you?
I'm fine. Doing great. Yeah, all
Yeah?
good. Thank you. And you?
Yeah, pretty good, thanks. Yeah, not too bad. Yeah, a little bit tired, but that's what having two kids does for you, isn't it?
Yeah. I know exactly what you mean. Yeah, I'm on the same situation
Yeah.
or similar.
It's a different plane of existence when you have kids.
Yeah, absolutely. Yeah, everything changes completely.
Mm.
You just wonder where did you, where can you find time these days to do the same stuff or even more?
Yeah.
When before you thought you didn't have any time for anything, and now,
Yeah, exactly.
Time notion of time just changes completely.
Yeah, it makes you realize, I think, like how non-efficient you were being before you had a kid. You know what I mean? And it's almost like I've now matured to the point where I'm spending any free time I have doing something useful. Like, so much time I must have wasted before I had children.
Exactly. That's probably how Einstein came with the relativity theory. He just had kids and
And then it occurred to him.
Yeah.
Did he have children?
I don't know.
Who knows? We'll have to fact check that one.
Yeah, exactly. He's not famous for that. I know he's married, but eventually. Okay. Yeah.
Right. So let's talk a bit about like your research and your work here, because actually, to be honest, it's a completely alien thing to me. I mean, obviously, I did a little bit of research, only very briefly, before you came here, trying to figure some of it out. It's to do with materials. Is that right?
Yes.
I'll let you elaborate.
Right. Where should I start? I don't even know. So I think that my most current project is that you're talking about probably is the ADDISONIC. This is a lab that was funded by Bournemouth University through Research England. So that's something that started. We started building it this summer. So everything is still ongoing. And it's a very exciting area in the sense that we try to predict the life of materials, especially novel materials like those obtained from metal additive manufacturing, for example, where you don't have predictability of properties as you had for other materials. And we do that in a very fast way, an accelerated way using ultrasounds. The technology already exists. I was involved in a project before when I was in the University of Lisbon in Portugal. And basically what we're doing is replicating and embedding new stuff in the lab we've got here to test those materials. So that's what it is. It's a fatigue testing, basically.
I see. So novel materials, as in materials that haven't been used in producing things previously. Is that what you mean by novel materials?
Yeah. So the thing is that now when we obtain things from additive manufacturing, they are printed, for example. So and you could print them, for example, with horizontal layers or vertical layers. Okay. And that will mean that you have what we call anisotropy, which means that the properties might be different in different directions. So whereas in regular metals, they are the same in all directions. So if you apply a load in the horizontal or vertical direction, the expectation is that they will behave the same way. When you 3D print them, that's no longer true. You can't just assume that. Then there are other issues like voids, defects that could be in the material. But that's one of the things. So in the past, you would be able to test alloys that are very well known, for example, EN8 or EN19. These are still grades. And you go to a datasheet and you know exactly what the properties are. There probably have been people testing them before for fatigue. So you know if you apply a certain cyclic load, how long it will last. There are then models to do that as well. So you could predict how long your part will last. This could be used, for example, when you do programmed obsolescence.
So what's that mean?
So so when you buy a light bulb in the supermarkets, although I don't work in this area specifically, but it's just to use as an example, it will say there that lasts, I don't know, for 10,000 hours. That's programmed obsolescence. They could have designed it to last for 20,000.
What's the second word you're saying? Sorry, program
obsolescence.
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 It's just,
sorry.
Sorry, no, my mistake.
No, it's my mistake. It's my accent. Is sometimes it's even difficult for me, as you can see.
As in, like, because Apple get criticized a lot for creating phones that have this built-in obsolescence, so that they intentionally, yes. The battery wears out intentionally after a certain amount of time, because you then have to go and buy another iPhone or whatever it is.
But that's actually, for me, when I talk to my students, so I'm a mechanical engineer, that's my background. Mm-hmm. And when I talk to my students, I tell them, for me, that's the perception of quality I've got. For me, quality doesn't mean that a product is premium. What it means is that it does what it says in the tin, which is it's been designed to perform in a certain way, in certain conditions, and to last for a certain period of time. So I give you an example. I had a car some years ago, and after 3 years, the first headlight bulb went off, and I had to put a new one. And it was, I don't know if can I say brands? Maybe it was
sure.
Bosch, which is a German brand, very famous. And I had it replaced. 2 weeks later, the other one went off again. The opposite side.
Okay.
So for me, that's the meaning of quality. So this is amazing.
So you were actually impressed by that?
I was impressed by that, because they basically lasted for the same duration, give or take 2 weeks. It's 3 years, and I think that was quite impressive. This is a good example for me to bring to the classroom. So that's,
I like that you've got that perspective. Other people will be going, "Oh, for crying out loud, both headlights in the space of 2 weeks," but you're there, impressed by the manufacturing standards.
Because when you design a product, you should also have in mind the obsolescence, the duration, the lifetime you want it to survive, because you might go out of business if it lasts forever as well. If you're selling washing machines, and then they last for 100 years.
Well, I suppose that's why corporations get criticized for it, in a sense, isn't it? Because obviously it's ensuring their own well-being over what some people might say the environment or whatever, or this sort of stuff. I suppose that's a debate in itself.
It is, and I think the good news are, I think people and corporations and the new generations are becoming more and more aware of sustainability issues, of the problems with waste, and the ADDISONIC is in that we want to contribute to low carbon emissions. So the other side of testing very quickly the materials, the other aspect of it, so the aspect of being able to test, so you want to, I don't know, to produce something, you want to predict how long it will last with a new material that wasn't tested before. So you want it quick, so that you get the information quick, so that you are more competitive, obviously, and it is a lot cheaper because of that. But the other side of it, which is a positive as well, is that we can test, because it's so fast, to extended lifetimes. So the idea is that we start testing, and industries are starting to be interested about that, on what we call the very high cycle fatigue regime.
Is there an acronym for that?
Yes, that's so. If you the difference in testing is that the machine we use operates at 20 kilohertz. Right. This is becoming standard. There is no standard yet. There is a Japanese standard, but hasn't been translated to English yet. But typically, they are 20 kilohertz. There are 2 reasons for that. Reason number 1 is that you can't hear. Most people can't hear it. If it would be operating at 18 kilohertz, you would probably hear it, and it's a very uncomfortable sound. Above that, there are constraints in terms of the specimens, because we built coupons to be tested. I can explain that a bit later, how we do that. And they depend on that frequency. So 20 kilohertz means that 20 cycles per second. So in 1 second, we are deforming a part 20,000 times in 1 second. To reach 10 billion cycles, we would need, in theory, 14 hours. So I've done the math already.
Wow.
In reality, you need maybe 3 days, because of some issues that exist with heating.
Yep.
But if you'd be using a classical rotating test machine at 30 hertz, which is 30 cycles per second, which is already slightly quick, it would take you, for the same test, working 24/7, 1 year. You just do the math.
Wow.
And that's the difference. So talking about a couple of days to 1 year when you want to test on these extended regimes. So there is some interest in that, because not only because of extending the lifetime, but this brings other opportunities in terms of markets. You could, for example, I'm working on the business of maintenance or extending the lifetime of something. So in maintenance, how it works is you are always trying to bring the reliability up. So what you try to do is to so something is wearing down, but then you could make something happen so that you bring back the reliability. So for example, an example is changing the oil in your engine, your car's engine. You do it every, 10,000 miles, for example. And the reason why is because what you want is to make sure that the lubricant you're using still has the viscous conditions it should have, that any debris that is inside, because there is wear, is washed away. You could still keep there the old oil forever, but the likelihood is that will wear down your engine more quickly. So what I'm trying to say is that there are techniques, and I was involved in a project where we did that. The objective is to treat materials. So this was a PhD student I had in another university, actually, but he was developing techniques to treat metals based in electromagnetic field treatments. And he observed a few things. One of them is that we can extend the lifetime of material with those treatments. The problem is, by how much? If you go to conventional testing, there is just no time to test and quantify that. So you need to go to these accelerated tests.
I see. Right. Yeah. So this accelerated testing, you're using high frequency
vibration.
Yeah. It was ultrasonic, you said earlier, wasn't it? Okay. And this is essentially vibrating I'm not a scientist, particles, atoms, something like that?
Yeah, we're vibrating I didn't bring any coupon. That was a shame. I forgot a specimen. It looks like an hourglass or a dumbbell,
right?
Like the shape. That looks something like that. If it is uniaxial, I've developed also for biaxial testing.
But this is a solid structure?
It's a solid structure, piece of metal.
Okay.
Yeah.
Right. Yeah. And then you just vibrate that at high intensities to see what happens when it eventually fails.
It develops a crack.
Okay, I see.
And when it develops a crack, it will eventually fail. Just breaks. It doesn't shut. It doesn't explode.
That's a shame. In my mind, it's like.
No, it was a crack. The crack grows, and
the crack grows, and eventually it would fall apart. I would guess.
In reality, typically, it doesn't really go down to that, because what happens is when a crack develops, the frequency decreases. So these machines are designed to operate in a certain frequency band. So it's between 19.5 and 20.5 kilohertz. So as the crack develops, the stiffness decreases. So the frequency, it's like when you have a guitar, your strings can go out of tune. And typically, the pitch never goes up, it goes down, because they become more loose.
Yeah.
They loosen
of course. Yeah,
a little bit.
Makes sense, yeah.
So, and when they are less tight, less stiff, the frequency goes down, the pitch goes down. And with the crack developing, it's exactly the same thing. The pitch goes down, and when it reaches the 19.5, the system stops. So you then can insist to try to break it, right. but it would stop when the crack opens up to a certain extent.
So I might have completely misunderstood here, but to me, there's like a machine, there's like a box that you put this metal inside in the middle.
Yeah.
And then ultrasonic waves get pumped at it. Is that right? Or are they put through?
No, the machine is the specimen has a screw. Is screwed to a machine. Machine has what we call I don't have any picture here to show, but it has an actuator, which is actually used for welding plastics. Then it has what we call a booster, which increases the vibration amplitude, and also has the fixture where you're going to place it on the machine to be held somewhere. And then you have what we call a horn, which is again to increase the amplitude of the frequency. And then you pop the specimen there. So you have a sequence of stuff, and the specimen is here. It's being basically hang by the horn. And then what it does, the machine makes it shake like that.
Right.
You can't see it. We have machines that we have a very high-speed camera, digital image correlation camera, that you might want to see. given your background.
I'd love to see that.
It's very high speed, and we can actually watch our specimens deforming at 392 kilohertz. So we're talking about 392,000 photos per second.
Wow.
So we need to have very powerful lights, LED lights, to be able to see the deformation. We painted the specimen.
Are they LED lights?
Maybe not.
I would question that only because my knowledge of lighting is that anything that's LEDs are blinking on and off.
You have to go
50 hertz.
Okay, but you have to go and have a look.
I will have to, yeah.
You have to go have a look.
It might be an incandescent light of some sort that's just glowing,
maybe
a filament.
I thought
because they're constant.
I thought this was LED, but we can.
That would be interesting to see.
You are obviously invited.
Oh, great! That'd be great. I'd love
to the lab to go and see.
Yeah,
it working. What it does is we spray the specimen with a white matte paint, and then we spray with black on top, or we use a brush to do a speckle pattern, black and white, and then when it deforms ever so slightly, the camera picks up the pixels moving, and you can actually measure deformation. Then you could show it deforming in slow motion. It's very interesting.
Wow.
So I brought here this paperclip just to explain what fatigue is.
Fab.
Because it's something that most people might not be aware of what it is.
Yeah.
And I think the paperclip, I don't know if the camera will pick it up, but it's the best example I can find. So what we want to know is, if I apply a certain load to a material, which we call stress actually, how many cycles will it endure? So what I'm saying is this: if I sit here on this sofa and I stay here forever, this is statics. But if you go to IKEA, for example, I don't know if you've ever seen the sofas or chairs being tested.
They're always a bit worn, yeah.
But they do. There is a machine.
Oh, they have a machine. I've seen the machines. Yeah,
I've seen that.
And opening and closing drawers and things.
Yeah, exactly.
Yeah, I've seen this,
what they're showing is fatigue testing.
Yeah.
So doing that wears down, and that's why we call fatigue. It's like getting tired. You go to exercise to the gym, and you get, if you do it once, it's easy. But if you do it 100 times, might not even be reached there. So the materials is exactly the same thing, well, phenomena is different. But the paperclip, how it works is this. So if I deform the paperclip, I'm just going to deform it a little bit so that I can do it. And I'm going to basically bend it, and I count 1, and I do 2, and 3, and 4, and 5, and 6, and this is taking longer. 8. So I count the number of cycles.
One, yeah.
So I count the number of cycles, which is, come on, paperclip.
You've got the world's strongest paperclip.
This usually works very well, but you get the gist of it. I think it's not even deforming well anymore. Oh well, this is the strongest paperclip ever.
It's a trick paperclip.
It's a trick paperclip.
I swapped it out before you came in. I don't know if you noticed.
Come on, there you are.
Okay, that must have been about what, 20?
I don't know, maybe
that was a lot.
So this is called low cycle fatigue. What I did, which has different, there's different phenomena happening then at high frequency, but the principles are the same. So now if I would apply less deformation, less stress, it would probably take me more cycles until it would snap.
Less stress meaning you're bending less
Yeah.
distance, for example?
For example, yeah.
Okay.
So it would take me longer for it to basically snap. So what we do is, the most basic stuff we do is to have what we call an SN curve, which is a plot. Vertical axis, we have the stress, the load, the force, if you want, but it's typical in terms of stress. And on the horizontal axis, you have the number of cycles. And then you know that stress you applied lasted, I don't know, 10 cycles. So you put there a dot on the 10 cycles. Then you start decreasing, and then you go, and suddenly you have a plot, and you can have an estimate. Okay, now I know if I want the life to be, I don't know, 10,000 cycles, I know that the stress is that one. And with that stress, you can then design the paperclip to.
So what you're talking about is the typical amount of stress a paperclip might be under when someone bends it to put paper inside it, for example.
Well, I'm just using this as an example.
Yeah, of course.
As an example, but could be. But if you want to use, I don't know, you want to actually do the same number of cycles, the same stress, but you want to double the life. So you might want to make the paperclip diameter
thicker.
But you want to do it optimally. So that's where the engineering comes.
Based on, are you talking about budget and those sort of things as well, and efficiency in production, all that
exactly,
sort of stuff?
all that stuff, because especially paper clips, if you multiply this by millions or billions, a little bit of increments will have a considerable cost.
Yeah.
So that's where, well, I'm sure you can design a paperclip. You don't need to be an engineer for that. But if you want to
I'm not sure I could, to be honest.
But you don't need to be an engineer. You know what I mean? It's just
yeah. But it's a lovely, simple example. I like that.
That's the one I use. It wasn't that successful, but because this paperclip was a trick paperclip, you swapped.
So are you unimpressed? I mean, how long does it usually take for a paperclip to how many cycles?
I don't know. It depends on how much you bend.
What I'm saying is, are you unimpressed by the manufacturing quality of these paperclips? Because the planned obsolescence wasn't consistent.
It wasn't consistent.
So whoever made this, don't buy paperclips from them in the future.
No, they're probably too good. I need to go and call them and say, listen, guys, you're losing money. You don't need all this material. No. I'll make you save some thousands of pounds or hundreds of thousands of pounds. You can make them thinner. They'll work.
Oh, that's crazy. Oh, that's funny.
Yeah.
Right. So like, what led you to this path that landed where you are now, testing this sort of stuff? Where have you come from to get to that point?
Okay. So that's probably a long story, but
you can start from the beginning if you like. Or...
I can start from the beginning the beginning is I was born. And it's almost there. My father is a mechanical engineer, and he's retired now. He's a professor, or was a professor in modal analysis, vibration and modal analysis. Ooh. And obviously, I'm not sure if this is obvious. It probably isn't obvious, but I always wanted to be a mechanical engineer all my life. I never wanted to be, I don't know, a policeman or... I never wanted to be that. I wanted to be an engineer. An astronaut. Never crossed my mind. Later, I thought maybe I should have tried to being an airline pilot or something like that. But until I went to university, I thought about computer science, but it was all very, it was on the engineering science side of things. So eventually, I liked physics and math at school. I was good at that, and I went to mechanical engineering. And while I was in my degree, my father was there at university, and he was doing research, and he needed basically cheap labor. And I volunteered for cheap labor.
It was more acceptable back in those days, wasn't it?
So it was a good experience. So I started by doing vibration testing in the lab. Wow. Actually involved in an European project, so I did loads of the experimental testing in the lab, which was quite exciting. I learned a lot from that. That put me in touch with people in the group, and eventually, when I started working, I mentioned about maintenance. I went to industry, working on maintenance plans of rolling stock vehicles. So I actually started in the industry.
Of what? Sorry, rolling stock.
Rolling stock, so trains.
Okay. What did you call them? Rolling stock vehicles?
Yeah, rolling stock is something that rolls, a stock that rolls on railways.
Okay.
Yeah, I think that's the term, rolling stock.
Maybe
yeah. Again,
no, it's just me. It's me. It's my ignorance to this stuff.
No, so basically trains, trams. So developing maintenance plans for that, wow. Which was.
And how old were you roughly at this time?
So I was around about 22 to 24. When I was 24, then there came the opportunity for me to start teaching. Ooh. In a polytechnic, and I wanted to try because of my father being in academia, and so I did that. And eventually, I started doing the masters. Then I did a PhD, and because I had that contact with experimental testing in vibration analysis, I continued that pathway. So I did my PhD in structural health monitoring of composite structures. So what you're trying to do is to assess from vibration-based patterns.
Yeah.
If you have damage and where it is. That was my PhD, try to locate it.
In what? In a material?
In a material.
Okay, wow.
So when you have composites like carbon fiber, one of the issues is the barely visible impact damage. So what is that? This is typically low to medium energy impacts that these laminates suffer. For example, in an airplane, could be a tool dropped during maintenance, or could be hailstone, or could be, I don't know, something debris that is in the runway and hits the fuselage of the aircraft.
Right.
The problem is when it is barely visible. What this means is this: if it is low energy, that is not sufficient to introduce any damage. That's fine. If it is so hard that you can see it with your eyes, that's fine.
You can repair it
like
easily.
A bullet. Oh, it could be too well. You don't need. If it is a bullet, you see there's a hole there somewhere.
Yeah, I think that's where it hit.
I think that's where exactly. The problem is when you can't see it with your bare eyes, but it might be
it's weakened the material.
Exactly.
Right.
But you can't see it because what happens is typically this type of damage in the outside you can't see it. It has a small indentation that is so small that in the whole scale of things it's just very difficult to find. But internally the structure might be damaged, and because composites are used as structural elements, that could be dangerous. So my PhD was about doing shaking the structure, not to the point of failure, shaking the structure lightly, and from the vibration patterns detect any differences in the vibration patterns and try to, from that.
So are you shaking it from each different axis to try and locate exactly where?
We can do that because there were plates. I was just shaking in one direction. So
Right.
we consider it's what is called plane stress. So because I was doing only plates. So
right. As in like China plates, like plates that you eat.
No,
you might think I was joking when I said that. I wasn't.
a plate is a structure where one dimension is a lot smaller than the other two. So that door over there could be considered a plate,
right,
or a shell. That's what I'm calling plate or shell. It's a shell actually. So one of the dimensions is a lot. So you have a beam. Is a structure like this ruler. There you are. I can probably use it again, but this is called the beam because two dimensions, the thickness and the width, are a lot smaller than the length.
Okay.
So, and then you have anything else. You have like this is a solid body, but this one here, this could be treated as a beam as well. It's very long, but this section is very small compared, so you could treat this as a line.
Even though it's cylindrical, it can still be treated as a beam. Yes,
you can, because you can do that because you have some properties you can deal with.
Is there a cutoff point? I mean, if I'm being pedantic now, at what point that becomes that transfer, or is it just a?
I think like rule of thumb is like 10 times smaller. That's what I would consider.
Right.
Rule of thumb.
I feel like I'm being educated. I feel like one of your students in
a lecture. That's what I say. Rule of thumb, 10 times.
Right. Oh. Okay, I'm with you.
Yeah.
Do you know my sister is a structural engineer now?
Oh, is she?
Yeah. Oh. She did her thesis on bamboo.
That's
as a structural material.
Which in the sense is it's studied like a composite material, like carbon fiber, because bamboo has fibers, long fibers.
Okay.
That's really an interesting.
She says it's very, very good, and I forget the terminology. It's good in what, compression, but not so good in
bending.
Something like that.
Is it?
I don't know. I don't want to get it wrong, but one of those things, or twisting. Who knows?
I would probably.
So you need to do a lot of things to it in order to be able to
say it's actually good in tensile and bend, because there are different types of load. So what I said to students is something like this shape. Well, obviously, or maybe a cylindrical one is better to say. I will call this, from an engineering point of view, I can call this either a bar, a shaft, or a beam. And they might be exactly the same object. But when I'm saying bar, beam, or shaft, I'm basically saying that the loads and the function is different. So a bar operates in tension or compression. A beam operates in bending. This is bending. And the shaft transmits power and basically twists.
Oh, okay. Yeah. So it's around those three axes upon which force could be applied to the thing.
And they don't have combination.
That effectively defines what its purpose is.
Yes.
Or its purpose defines what you call it.
Yeah. When I give it that name, I'm actually saying implicitly, what if it is a beam? I know it's bending. Yeah.
So a beam in a house, for example, what we're saying is that there's forces being applied above.
No, for me, it's like this.
Yeah.
This is a beam or this. So, if it is vertical, I call it probably a pillar.
Yes.
Or a column.
Yeah.
Because it's going to be compression.
But
I don't call it a beam. Like it could be exactly the same object.
Yeah.
But because the position and the way it is working is different, I give it a different name.
Yeah. I get that. But what I think when I think of a beam in a house, I mean, you wouldn't put. I used to be a carpenter, so I used to build.
Yeah.
So for example, if you were putting a beam like a piece of say 6x2. You wouldn't put it flat like that because it would bend in the wrong way, but you'd put it upright like this because then the force being applied.
Oh yeah, absolutely.
So when you were saying a beam bends, this is what I'm getting confused.
Well, so what you're talking about is
because you don't want a beam to bend, do you?
No, obviously not. So I'm doing this because I'm strong enough for that. But if I do it like this, you won't see anything.
Yeah.
And this is exactly the same object again, the different position. That's a good point, actually. What we are changing here, it's the same object, same geometry, same material, same loads being applied, but the stiffness changes considerably if you put it that way or that way, because what we're changing is what we call the second moment of area of the cross section.
Right.
So this second moment of area about the neutral axis is a lot larger than this one, and so that's why I can't really bend it, or I'm bending it, but I can't see it.
Yes. Yeah.
It's just very, very small.
Fab. I'm glad we cleared that up. So you were born in Portugal, is that right?
No, I was born in London.
Oh, were you? I think we might have had that conversation before, actually. That's rung a bell when you said that.
I was actually born in London too, but my parents are both Portuguese, and I went to Portugal when I was 1 year old,
right?
Probably.
So what was your childhood like?
It was nice.
Generally speaking.
It was good.
Yeah?
Yeah. I can't really complain. It was a very, very, very good childhood.
Did you read a lot when you were young? I had a guest on yesterday who's professor in our department.
Yeah.
And he just said he read all the time when he was young. So
I have to admit that I didn't read a lot.
Yeah.
But I was.
You're more of a practical kind of person, I guess. I'm
more practical, and I think I was quite a computer nerd, or I don't know if I can use that word, but
sure.
I had a Sinclair ZX Spectrum 48K,
which is
in
the
computer. 80s. It's a computer.
Right.
I've seen a photo of it somewhere. There is a photo somewhere in the university. I've seen it today.
Really?
Yeah, with the rubber keyboard. And I used to code in BASIC at the age of 8 and 9. I was doing simple games, coding simple games. So that was my I did a piano with the keyboard. So you'd play with the keyboard and you could play different tunes. I did games like swapping letters. So you would write imagination, which is the word there, and then it would swap the letters and you had to guess. I don't know. I did simple stuff there.
That's quite impressive. At age 8.
8,
I mean, it's
9,
encouraged these days to get into coding, isn't it? But back then, I mean,
because with the Spectrum, you had no choice really. To load a game, you had to put loads, and then it was inverted commas, and then push enter, and it would load the game, which took forever. But there was a magazine those days that they brought every week. So my parents would buy it for me every week. They brought simple codes for games, little games. So I would go and code it myself to play that game. Instead of buying a game, I would code it. And while they were copying the code because you have to type.
So you were creating the game because instead of buying the game.
Well, we bought games as well, but there were simple games in that magazine. There was that magazine. It brought code there, and you could.
That's really cool.
Yeah, I loved it. And I would go and copy it, basically type everything in the computer, and then would play it. And while you're doing that, sometimes you make mistakes in the coding. There are bugs, and then and to fix them, you need to decipher what's there, and that made me learn a lot. So I learned basic by myself like that. And then you start doing your own stuff. Then you start trying to crack the other game. So the game is loading and you break, and then you try to see the coding inside the game. And you start developing further, and then to see how did they do this, and you try to break the code to see if you can see inside.
So from a very young age, you developed this sort of analytical mind and this way of like thinking logically about things.
Maybe.
And I feel like that's probably, carried you through to some extent.
Yeah, that's
to what you do now.
That probably is the case.
Yeah.
And obviously my parents encouraged me, or never discouraged me. Well, they would buy the magazines. I couldn't do that myself. Then there was I got a book as well, full of examples of. So it was just this thick. It was just codes for games. So you would go there, write it yourself, and then play. And most of them were rubbish, but I was just keeping myself busy and having loads of fun. It was then I did with those games. Sometimes some we bought. There was one which was this was bought. But if this says something to older generations, there was one called Check Yak 2. And myself, my sister, and my father, so this was an activity we were doing together. We built, it's a shame we don't have this anymore, everything by hand. We designed the whole map. We sketched the whole map, which was probably on a 0 sheet of paper, with all the levels, everything in color by hand. Everything.
So pen and paper, sketched everything out.
So this was kind of an activity we were doing on the weekends together with my father. Like,
wow.
And over weekends, and you just wonder these days you would never do something like that. But we were busy and socializing, and it was like a puzzle.
Yeah.
Because that game you had to build this is the story of the game. It was an arcade game, I think that's what it's called, but platform based. But the objective was to build an Easter egg with a toy inside. So you had to collect milk, sugar, chocolate, and then the pieces of the toy. Right. So it was 4 things you had to do. But the map was really huge, and there were 2 routes you could follow to do that. When one was harder than the other, and so. But on those days, you couldn't save. If you die, you would die. That's it. Start all over again.
It was quite traumatic back in those days when you lost.
So we made the map so that we knew exactly what to do in each screen.
See, the skills that's given you, though, that was just sort of stripped away with the invention of the memory card or whatever it was first, and now, internal memory that you can just save and try again or whatever, reset.
So it was great fun because we did that with my father, so it was great fun. You would do it on... Yeah.
That's kind of like the idea of like mastery and stuff, isn't it? Just doing something so much because you enjoy it that eventually you become a master of this thing, and, really...
I was doing everything for pleasure, and the coding as well. And I have to say that when I went to mechanical engineering, I wanted to be, I was really, really about to go to computer science, but this was in 1995. And by then there were no mobile phones. The iPhone only appeared in 2008. That was yesterday. If you think about it, it's yesterday.
Crazy, doesn't it?
My first mobile phone I used to call it a brick. Like a brick, the brick, and this was I was on my 3rd year at university, and the only thing it did was phone calls. It didn't even have the snake. My first mobile phone, they didn't have anything.
What was it? Can you remember what?
It was an Ericsson.
Oh, Ericsson, yeah,
Ericsson.
Crikey.
That was
Are
my
they
first.
Still even making phones?
I don't know.
Probably not.
I don't know. This was probably 1998 or.
And did it have Did it have just like 9 buttons, like the numbers and the 0, or did it have? Because you remember BlackBerry came out and it had every single letter on a keyboard.
No, mine had the asterisk and the cardinal, the numbers, and then the green button to make a call. And
but mind you, you couldn't text at that point anyway, is what you're saying. So it's not like you needed the letters.
My mobile phone. Well, it did. I think you could text, but
you used to be able to page.
One had ABC, D, F, so you would.
Do you remember pages?
I got one of those as well. I had one of those.
I had one of those. What was the? I mean, you couldn't send messages back on them, could you? It was just a way for people to contact you. I seem to remember.
No, you could send messages, but you had to call an operator, and you have to say, "Honey, I love you." It was a bit. It could be embarrassing, like you're talking to someone else to say, "Can you please write this? You're very hot."
like a mediator in the middle of your
relationship.
Yeah,
you're like, oh my God, I'm like, so you wouldn't be able to, you were like a little bit constrained about what you were saying.
It's crazy.
There was someone in the middle, and then they would text that message to the person who had the pager or beeper or whatever it was called.
Let's hope they don't spell the name wrong or something. You get in trouble.
Yeah, exactly. But yeah, so I eventually chose mechanical engineering, as I said before, because my father pushed me a bit for that.
He
because
did, right.
I was good in math and physics, as I said. I liked that. Computer science by then wasn't. If I would have been to that, I would probably be rich now, because in IT,
it would have boomed at just the right time.
From that generation, yeah, exactly. It was the right opportunity, but I'm happy with what I'm doing. I do loads of coding. So the machine I developed in the ADDISONIC and in Portugal as well, I did all the coding, all the control of the machine. So
really, wow.
Yeah, it receives signals and then it has to control the amplitude of vibration, has to measure the temperature. When it reaches a certain level, it needs to stop. It needs to start a cooling system. So I'm doing coding.
So coding in that sense is basically like, if this happens, this happens. If this happens, this happens.
Yeah, it can be. Yeah, it's the basic for while loops.
What did you call it?
For and while loops.
For while loops.
So the while loop is, for example, while the temperature is below, 40 degrees at that where you're measuring, continue vibrating and acquiring the signal. When it reaches 40, then stop the while loop and then go to another loop and start the cooling. While the temperature is above, 20 degrees, continue blowing air to cool it down. When it reaches 20, go out of the while loop. So it's called a while loop. It's an if condition, if you think about that, but it repeats.
I see.
Goes back until the condition is met.
Is this part of the problem you were saying earlier about cooling and stuff? You said there's a problem. You can't run this machine 24/7 because of cooling. Is this part of what you're getting at now?
So that's the thing is materials have something called so there are three properties in vibration that are quite important, which is the stiffness, as you managed to talk about quite well in a good example. There's the mass. It's really important as well. And there is the damping. The damping is this. So if I shake this beam, it will eventually stop shaking. And that's because of damping. And damping is a mechanism of energy loss. And eventually, energy will all be converted into heat. That's what happens. But I can't really feel the increase in heat here.
But if you did that 1,000 times, maybe you'd.
If you do it very, very quickly in materials at 20 kilohertz, you will see the material getting hot. And when the machine is on the beta version, so when it's not really working as you intend, so temperature reached that level, but the while loop continues spinning around, it didn't stop. That's why I have there an emergency button. You will see smoke coming out of the metal and turning blue, which is oxidation, like quenching, and you don't want that to happen.
I guess that makes for an unfair test then, because I suppose when materials are hot, they respond differently to vibration.
Yes, right. Very good.
Thank you.
No, yeah, definitely. So that's why we need to. So we can actually have the downside is we need to have a range of temperature which is relatively limited, so that we don't have those differences visible. But the advantage is, if we want to also test it in harsh environments at higher temperatures, we could do that as well, very easily. So, it has. So we need to cool down the specimens somehow, because of what you just said. It does change the stiffness and the properties and the life, etc. The ductility.
Is that a problem? I mean, to me, I'm thinking it must be heating up just after, say, like 10 cycles or whatever, a little tiny fraction of a degree or something. At what point does it become a problem, or is it always a problem, even at the? Do you know what I mean? It can't just go from cold to hot suddenly. It must be a
no, but we're talking about 20,000 cycles a second. It's like it's doing this 20,000 times in 1 second.
You can't even fathom that. I can't even really. But this is why we can't even see it happening.
It's really, really fast. So it's
so what I'm saying, after 1 second, does it not heat up just a tiny bit? So is that a problem then for testing, because it's never truly a reliable test in that sense?
Well, it probably takes a few seconds until it reaches it. Yeah, it's feasible. Yeah, it's feasible. It doesn't become a problem, no. But obviously, the higher the stress you are introducing, the quicker each sequence of testing has to be done. And then obviously this brings other questions, which is, well, you know, there's something called the overshoot. So if you, I don't know these days, but in the past, I remember if you have a sound system with a good subwoofer, you turn it on, there's like bump sometimes, or if the amplifier is not very good, or if it is valve type of amplifier. Have you ever seen that? You turn it on, there's like a pump. That's an overshoot, and like a pick. And that's something that with the stop and start, that's an issue we have. But yeah.
So what causes that?
This is a mathematical. It's when you go from one state to another. So from zero to there is we call it an overshoot. It's like if you give an impact to a structure, you'll have a transient vibration. So it's a mathematical concept. It's I'm trying to explain this in layman terms. If we would explain this mathematically, it was easier but harder because it involves differential equations.
Let's not go there with me.
I
mean, go ahead if you need to.
But it's like when you go from. I'm going to try to use these words. So when you flick a switch on the wall. It's like giving a small impulse because you're changing from a steady state to another steady state, from here to there. There is an impulse. As slow as it is, there is always it's an impulse.
Sort of like a momentum.
Yes. So it's like pushing something. So it will bounce more and
so it might go up first and then drop back down.
Yeah, exactly.
Oh, I see. Okay.
That's called an overshoot.
Right. Nice.
And that happens always. So when you flick a switch, so there are obviously ways to reduce that, control that, filters, I don't know, whatever, making smoother transition. But there will probably always be there something. I think it is residual and it's not important, but there you are. It's a difference from having everything in steady state, continuous forever, or on off, or on off, on off.
So this is a problem with did you call it the ADDISONIC?
I don't think it's a problem because we're talking about...
But it happens with that as well.
Yeah, it's once every hundreds of thousands of cycles, right, which is irrelevant.
Yeah,
that's the thing.
Fab. Yeah. So you have a son?
Yes, I do.
Who is 5?
Turning 5, yes.
Turning 5. Are you in the back of your mind, are you hoping he gets into this sort of industry as well? Like you said, your father sort of pushed you into.
Well, so
will this just be a generational thing that lasts forever? You know, my father before me was.
I don't really, on one hand, obviously, but when he shows an interest, obviously, I feel like yes, he likes that. So one of the things he really likes to do. And it's one of those things. I don't know if it was me who influenced him or if it was him who saw that I liked that, so he pushes that as well, and is like doing construction stuff like Lego. He loves Lego. He loves doing Lego with me. So we play a lot with Lego, for example, or constructions with wooden blocks. He loves doing that with me, doing domino or doing a building or. And I'm not really sure if that's because he sees that I'm also enjoying and then he pushes to do that, or if it is something that is naturally embedded in him. I have no idea. I haven't. Maybe what he sees is, I want to play with Daddy. I know he enjoys this, so I enjoy it as well because he's happy and he makes it fun. And so so in a way, when I see that he's quite good with Lego, I feel quite. Oh yeah, he might be an engineer.
Sort of like a proud dad moment kind of thing. Yeah.
But any advice I would give him is be a doctor. Or a lawyer.
Right. For the money, you mean?
Yeah, exactly.
Here's a question. So I used to play Lego with my dad when I was young as well, and that was when I first sort of started to understand that bricks, for example, should be laid so they're lapping over each other, and like that. Do you do the same thing when you're doing Lego with your son? Like, make sure it's engineered correctly.
Yeah. He's still very young, but he starts understanding. So sometimes he likes to do. So we build the stuff based on the instructions, and then he wants to shatter everything apart, and then he wants to do his own creations.
That's great.
But typically they become a little bit fragile, and say you need to add a structural element to that. So I say that, and it's my wife feels that you shouldn't be using those words with him. He might be bullied at school. And then sometimes so what happens is he sees me doing that, but then he can't really get the gist of it yet. He comes to me and says, Daddy, we need to add structure to this. Can you help me, please? It's like snapping.
Yeah. And
you need to put a brick on top because they need to be out of phase precisely to get that stiffness. So he comes to me, oh yeah, and he does it as well. Because you have that.
That's quite amazing.
He loves working with tools as well. So when I build IKEA stuff, he knows how to. So one thing he does that probably, I don't know if social services will come after me after saying this, but I've explained to him the risks and everything, and I never had any issue. Touch wood, changing the batteries of toys.
Oh, fabulous! Yeah.
So they always bring that screw for the kids not to touch it. So he goes and he wants to unscrew it. Yeah. Open it.
Is he good with a screwdriver? Can he do that by himself? Undo the screws?
He now can do it.
They're very small screws.
He can do it now by himself. If they're a little bit tight, I need to loosen them a bit so that he can do it. But he likes to do that. Take out the old batteries, and then put the new ones. Close it down. He never put anything in his mouth. No. That's wood exactly. And I think now he's turning 5.
Yeah,
that's already gone. But he loves doing that. He loves putting, and when he started wanting to do that by the age of maybe 3, he would be like crying if I wouldn't allow him to do it. So so I have to. He wouldn't be able to take the screw out, but I would do it for him, help him, and then So he likes to do those things. Yeah.
I think that's fantastic. That's sort of like, handing the reins over to them as much as you possibly can at an early age. Yeah. I do the same with my daughters to a certain extent.
And I think it's because they see we are having fun as well. I think they probably understand that's probably a good way to connect with us as well. When I build loads of stuff at home, and I'm very proud of something we did. For someone like you, it's probably going to be insulting, and probably you're going to think it's not insulting, but you're going to think it's probably horrendous. But we retrofitted 2 cabinets from IKEA on a wall around fireplace.
Nice.
So they were a lot longer than the fireplace. So I bought all the kit, and I learned that IKEA furniture is cardboard inside.
Yeah, it's really flimsy.
What's this? It's cardboard inside, like hexagon. It's quite clever in a way. Yeah. But my son...
Well, IKEA has optimized their, cost for what is it? I don't know.
It looks much better than what it actually is. But he helps me building the stuff, putting the screws, and what he really likes to put is the wooden dowels. Place them there, and then he goes with a wooden hammer, and he back. Yeah, likes to do that. So because we bought our house a year and a half ago, where we did loads of work. We painted the house, built IKEA furniture, made some stuff or adapted stuff as well. And he was there around, and I gave him some simple tasks to keep him busy as well. and make him feel that he was part of the joy.
Yeah. That's brilliant.
Yeah.
So what does the future hold for you? Where do you see yourself in 5 or 10 years time? Hopefully retired, he's going to say.
Hopefully retired. Well, I'm always wishing that I win the Euro Millions. It just never happens. I play every week, but it never happens. So I'm currently an associate professor in structural dynamics, which is something I haven't mentioned yet. Yeah, I hope that the ADDISONIC grows. We are now having a postdoc joining our team, maybe in March. I obviously, as part of the career, I intend to be a professor, and who knows? I'm also head of the department of design engineering.
What do you need to do as far as you're concerned to become a professor? Do you know? Is it clear?
Yeah. I don't think I don't think I'm too far from that. It really depends. There are two areas where I'm investing, which is research and leadership. And so, yeah, I just think I need to do a good job. But there are some metrics we've got in terms of research. It's about publishing in good journals. They're typically, if other researchers are listening, they should be looking at journals on, if it is in scope, was in SJR quartile 1 or quartile 2, which is also important for research excellence framework. Getting also partnerships with industry, because we also want to do stuff that has a meaning to the world and can have applicability and has an impact. So that's the other way to measure is impact. So if I'm just studying vibration because I think it's cool, it might have no impact or no meaning to someone else. So the idea is to make sure that we're doing stuff that has a meaning to others, to society, to businesses, to whatever. And the other thing is that we need to ensure is that we basically cooperate with others internally as well, not just externally. Build teams, networking, and have some fun, I think, with what we're doing. I think that's we live here, I don't know, 8 hours a day or more. So I think
it's a third of your life, isn't it?
A third of our life. Yeah. We have to work with other people, and I think the thing to do is to just get advantage of that. Different cultures, different people, learn from that and have fun. I think I think that's the thing. It's to try and have some fun. So those are the three things I think is to, in terms of research, try to publish. To research that has an impact, so has to have economic benefits, so for funding as well, and have fun, I suppose. I think that's
That's very nice. I think we should end it there. Yeah, that's a wonderful message to end on.
Yeah, okay.
Do you have anything else to say?
No, I think I have so much to say.
Well, you have to come back on us sometime.
I didn't use this until the end. I wanted to explain loads of things.
Oh, go for it. No, go on. If you've got more to say about the ruler, I mean, I'm all ears.
No, I brought this as a purpose. No, it's just to explain the principles of the machine. But that's probably
go on. We have time. How long have we been going? Okay, we're not even at the hour mark yet. Go.
That's probably boring now.
No, go on. No, I'm all ears now. You've got to do it now. We've started.
No, just to explain one thing that is differentiating from the type of test we do is that typically on classical testing, you have a machine which you call a universal test machine or a tensile test machine or rotating or bending, whatever. If it is tensile test, you have something, you have the shoulders on the specimen called the shoulders, and you have something that holds the specimen on this end, you have something else that holds on this end, like my hands. Now what you do is stretch and compress, and then you do this.
What's the degree to which you stretch, or does this vary depending on the test? I mean, how
depends
far?
On the material, depends on how ductile the material is.
Right, okay. So with a metal, I mean, obviously it's going to probably differ between the metal as well.
Yeah.
But are we saying like a millimeter? Are we saying a centimeter? What's the, or even less than that?
On a coupon this size, less than that.
Even less than a millimeter.
Yeah. So my coupons, that's a good question. So how much are the form? They are this size.
Okay.
The specimens.
Oh, because I suppose the actual size of the thing would vary.
Yeah. So the specimen is like this: a steel specimen, an aluminium specimen, titanium specimen is roughly this size. Okay. We're talking about 10 centimeters to 15 centimeters long.
Mm-hmm.
The diameter at the shoulders is 10 centimeters, and at the center is 1 centimeter, sorry, at the shoulders, and 3 millimeters at the center.
And it's this hourglass shape that you would describe.
So it's like pinky finger, the size of it. Yeah. So the amount that we vibrate, it deforms, is in micrometers. So you can't really see it. It's microns.
What's a micro? So I can visualize this. What is that as a fraction of a millimeter? Let's say.
It's 1,000 times smaller than a millimeter.
Right. Okay.
So thinner than a hair.
Mm-hmm.
So that's how much it deforms.
Wow.
And on the ultrasonic fatigue testing machine, you don't use two grips to deform it. Just fix on one, and then it relies on vibration. And that's why I brought this. One of the reasons is what we do is, let's say I have this ruler here.
Yeah.
And if I do this, it's vibrating at a natural frequency, so which is low like this. If I increase the stiffness of the ruler, so this increase, it is quicker. So these specimens are designed, I play with the stiffness and the mass so that they work like tuning forks, and they are vibrating like this at 20 kilohertz naturally. So if you would hit them with a hammer, they would vibrate like this at 20,000 cycles per second. That's the principle of operation. So they don't need anything holding them on the other end. They will just do it themselves. So the fun thing about this is trying to explain to people that's why I make the difference between load and stress. That's one of the differences. Typically on a tensile test machine, you actually load it, you apply a force to get the stress there. These machines, the load in theory tends to zero, but you still get the stress. That's the beauty of it.
That's the geniusness of it, is it?
Well,
so how?
It's based on modal analysis. I see. It's a different way of thinking. So when the funny thing is when you are thinking about engineering in terms of statics, like a static or quasi-static load that is being applied, or dynamic loads, so something that varies with time, it can change a lot the way you model the reality in the world if you are doing it in terms of dynamics or statics. That's just a curiosity.
I could talk about this stuff all day.
Yeah,
I'm probably still not fully understand it.
Well, it's like. So the thing is, like, if you are,
I'm gonna have to come and see this for real one day.
If you are pushing your kids on a swing, your daughter, who is now 6 or 7,
6 soon, in like next month.
If she's on a swing and she's not doing the work, you are pushing her, and you're pushing her as far as you can until you reach a certain amplitude. Let's say it's a big amplitude. When you are keeping the motion, you are doing the force at the same frequency as the motion. You don't need to do a lot to keep that amplitude. But if you would grab and hold her statically, you would need to do a lot of force to keep her at that position. It makes sense?
Yeah.
But the motion is still there, or that angle is still achieved, if that makes sense. So because dynamic, you change the position, obviously. In statics, you keep it there. If you'd go now slowly in statics, you do it like this. This is quasi-static. You need a lot of force. Whereas if you are pushing slowly, as long as it is at the same frequency of the motion, as long as it is tuned, the force is small. You don't need to do a lot of effort to get the motion. So those are the principles.
I can understand that.
Yeah, that's
a nice analogy I can get with. So I'm curious.
You can cut this.
No, I'm going to keep. No, definitely keeping this. I'm very curious now that you've said that, as to wonder whether you, in your day-to-day life, see the world in this way. Are you thinking about these things when you're pushing your son on a swing, or do you see the world in this way?
I think
to a certain extent.
I think sometimes I feel quite surprised. The world surprises me when I look to something and precisely. I can't now give any example specifically, but then I know there's something and you go, oh, there's a nice example of something happening.
Well, you said one earlier about your headlights in the car and stuff like that.
Headlights in the car. There was this is not mine, but this was someone who worked in the same field I met many years ago, which was she really understood the phenomenon of resonance, which happens in mechanical structures, by cooking a soup. which is a funny thing. It's like
so. This is essentially like
so
the liquid heating, which is actually causing vibration.
it was in the blender.
Oh, in a blender.
Yeah.
What?
Not the blender. Not the, the how do you call it?
On the stove.
No, the thing that
microwave.
No, it's a blender in a way. So you have a pan with the soup inside, all the vegetables, and you want to blend everything into
I guess it is
a mash
blender, isn't it?
Maybe it's a blender. It's the handheld blender.
Yeah.
So she was doing that.
Okay.
And when it reaches a certain point, it starts splashing around. So the amplitude increases, and she couldn't understand resonance. So, well, anyway, what I'm trying to say is that sometimes there are things in real life that we wouldn't think about, and suddenly you relate with those things you are actually studying or doing or
And I think there's a whole lot of beauty to, and you can find beauty in anything in life if you understand it deeply enough, I think.
Yeah, well, that's
like if you can see the patterns behind, a boiling pan of water, it's suddenly not a boring boiling pot of water anymore.
Yeah, from my perspective, I like to think about things in these terms. It's a little bit like Sherlock Holmes, like the research side of things, trying to understand why things happen. So I think that drives a lot of the type of life I'm doing. So when you asked why I ended up doing this, one of the reasons is because obviously I had my father who was maybe I have the Oedipus complex unresolved. I don't know. But
you need to become a professor, don't you, to fulfill that? Yeah, is that what you mean?
Yeah. So, but in academia, I can do everything. I can be an engineer. I can keep in touch with the younger generation, so I don't get a lot older.
It does help with that, doesn't
I can
it,
do research. Yeah, I can do research. I can do management. I can do everything. So I found in academia I could do that, and what it's really interesting is to try and find responses to stuff. That's what you try to do. You have a question about something, and when you find the answer or when it makes sense, it becomes a lot more interesting from my perspective. So I think you make a good point on that. So suddenly, now I understand this. So it's now I have an interest and I want to learn more, probably.
And a different perspective on life. When you learn, you change.
Yeah,
you transform as you learn.
Yeah.
So to me, it's also fascinating that there's people in this, just in the whole, everyone has a different perspective based on their knowledge base.
Yes.
So you're walking around looking at things in a completely different way to what I might be, and to what everyone else might be.
Yes. No, I understand exactly what you mean. So when I'm an engineer, I'm wired like an engineer. I did my first degree.
Wired is a good choice.
Yeah, exactly. I'm wired like an engineer. I think like an engineer. And sometimes, obviously, engineers are the best people in the world, as we all know. And I'm not biased, but but I'm joking, obviously. But sometimes I struggle with certain things. And I remember I eventually had the opportunity to do an MBA. Masters in Business Administration. Obviously, when it came to finance, I was the best in class, numbers and stuff like that. It was really easy, and for me and some of the people there who were from different backgrounds were struggling a little bit more. But then it reached a unit called, and that's what you're saying about change. It was called Leadership and Change, which became the most important module I did. At the beginning, I couldn't understand it, and my first coursework I failed. I got 45%, which at master's level is a fail. And that was what happened. So I went to the lecturer and I wanted an explanation. I don't understand. Well, I got this. I think I did a very good job. So the job was to do volunteering work at a museum in a group. And we had to talk about it. So as an engineer, I did everything like an engineer. This was the group. We had these tasks to do. And then we had to so basically we had to inventorize stuff that was in a shed, stuff like that. So this person was responsible for this task. I was responsible for that task. Everything very descriptive. I go to the lecture and yeah, of course. So first question, why did you join into this group? Well, because it was just the people I was working with and I get along with them. And well, I didn't mention anything on that. Why would I mention that? Why are you writing in the third person? So we engineers, we write in the third person passive voice. So instead of saying, I went to the, I did this experiment, I say, the experiment was done.
I see.
I always write like that.
Right.
But you should.
You take the person out of the thing.
Yeah. So no, we wanted, this was a reflective piece of writing. We wanted it to write in the first person, which for me was like, first person. There you go. I go, well, here you say that this person took the leadership, because it was on leadership and change, of this task. Yeah. What did you feel about that? I go, what did I feel? What do you mean feel? Yeah, what emotionally? Emotion. This is a report. I should have no emotions. Then I understood that in social sciences, things are a lot different. And they can be very important as well, that you have these reflections, which I knew nothing about, even after having a PhD. And I realized that being constrained to that box, that world of engineering, where I only deal with engineers and think like an engineer, is actually limiting me quite a lot in terms of the way I see things and perceive things. And then I managed to change. And on another coursework, I managed to get 75%. And I took a completely different attitude and approach to that. And I struggled to reach to that point. And it wasn't easy for me to write that piece of work. The way I wrote it was very, very, very hard.
Did that transform you in your everyday life as well? Did it encourage you to think differently or
a lot,
or feel?
A lot. I don't know if I managed to succeed in that, but at least I'm aware. I have that awareness.
I mean, to me, you come across as a very expressive and kind of, it seems to me you have easy access to your emotions.
Yeah.
So maybe that was part of the learning curve for you to get to that point. But, when you think of an engineer or a mathematician, you think, quite rigid and shy, but you don't seem like that whatsoever. So
no, yeah. So I think, as I said, I think this unit I had, leadership and change, in that MBA, was definitely, now that I look back, was the one that had the greatest impact in me as a person. And I couldn't understand initially. At first I thought, you can't teach leadership, change. So that was the attitude I had at the beginning. Oh boy, I'm going to wishy-washy stuff. I'm going to, and in the end, it was the one that had the most meaning, and that's because I changed, and I could only get that a little bit later. It's a process. I think it was really important for me. I tried to put that into practice every day and with my life as well, but I don't know if I succeed.
Do you see some of that in your students that you have now as well? Perhaps needing to be in touch more with that side?
Yes. I see that a lot. I think that's we do try to tell this to students as well, to give them these soft skills. But some of the students really struggle to understand why they need to do that, because students who go, especially those who go for mechanical engineering, what they really like is more practical side of things, like building something, or the mathematical, analytical side of things. And when you are doing an analysis of data, numbers, for example, you have to be objective. You can't be subjective. So all our type of research and projects, what we do is all about being objective. We want to have no subjectiveness in anything. But that's because you're dealing with things like numbers, or, this structure, it vibrates. What's the frequency? That's a number. It has no feelings. And suddenly we ask them to, that's why we encourage them, and we have assessment that is mandatorily made in terms of teams. They need to work as a group. And so I said to the students, you don't really need to all be doing the same thing in the team. What you need to do is to work as a team. You need to interact, because that's the whole point, is to put that subjectiveness like on the creative process. If you're designing something, we are the Department of Design and Engineering. If you don't have that subjective side of things, how can you be creative? If you're just objective, you're just making boring stuff probably. So you need to put your own personal experiences share them across the table so that you can actually develop something that could be more interesting and competitive. And I feel like I've been too many years not doing that, and then you start being wired in a way that that constrains you. It's a limitation. I'm talking about myself personally. Obviously, I can't talk about other people. Other people might disagree, but certainly for myself, I became too hardwired to the objectiveness of engineering.
Right. I suppose whatever path you go down, though, you're maximizing your potential in one sense, but also limiting yourself in another. Because, you know, you could say the same for someone on the opposite side of things who's very in touch with their feelings, but then has no kind of sense of objective reality or whatever. And I think maybe on our degrees in media, you know, we attract quite creative people, generally speaking, or at least a portion of them are fairly creative. So they maybe have problems with when it comes to writing and referencing correctly and all this stuff, because it's not wishy-washy and artsy-fartsy enough for them. Do you know what I mean? And maybe, you know, across the road at the Arts University, it could be even worse for some. And I mean, maybe I shouldn't say the word worse, because it's not necessarily about better or worse, I don't think, but it's just
I have
differences.
I have an experience many years ago. There was an exhibition in architecture, and so the university where I was the faculty where I studied was an engineering faculty, but they decided to create architecture as well, because they were saying that other faculties of architecture, they were too artsy and they didn't have the engineering understanding of stuff. What I liked about that was also an epiphany for me in terms of the creative process. And I realized we as universities, sometimes we take the risk to be constraining a lot the creative side of things. And the reason why I noticed that, because the exhibition was very well laid out. It was from the first year to following down to the last year of studies. So you have these models made by students, cardboard models and stuff like that. And what you saw was this: the first year models were all different from one another. From my perspective, because I'm not an architect, to the final year student models, they all look the same to me. They follow the same trends, the same fashion, the same lines, same type of stuff because they've been constrained to what's been current and done today, what is most fashionable, probably. I don't know if this is a good word. So I just wondered if we are not constraining too much the creative process because of that. You just could see it. It was,
I think there's an element of that, or the risk of that in all education, isn't there? Especially as we test students with the same assessment brief at the end and the same people doing the marking at the end. I think there's a risk to that, isn't there?
Yeah, absolutely. I definitely agree with that. Yeah. That's really a good point. But the reality is we are all different people. And sometimes it's difficult to explain to some students that, and that creates problems. It's like, my supervisor said I shouldn't be someone ask a question. So they usually do it, you know, in such a way that they ask you a question. Oh, do you think I should be doing this way? And I go, oh yeah, I agree with that. I think you should do it this way. And I go, my supervisor says you shouldn't be doing that way.
So they caught you out.
And what I usually say is, listen, we are all different people. Who is marking your report? So and so. So if you want to maximize the chances to have higher marks, the other person
this is a real problem I have when it comes to marking myself, especially when we're marking things like films here. I mean, we have a set list of assessment criteria that we have to mark against. But even within each of those assessment criteria, there's an element of subjectivity as to whether, you know, for example, with a film, it might say like quality of camera work. It's like, what does that really mean, though? Do you know what I mean? So there's always that element of subjectivity, and that really bugs me, to be honest, when I mark things, because I think students look at their final grade and feel like it's a judgment upon themselves or something. Yeah. But all it is our best shot at interpreting the assessment brief and the criteria and providing something back, because that's what we have to do in a university setting. Yeah. I mean, if it was up to me, we would get rid of assessment altogether, probably. But I know that's not possible because then why do people come to university at all?
It's a philosophical question. Yeah,
it's a
philosophical debate, I suppose.
I mean, especially so in the creative. From my perspective, it feels like in more of an objective thing like engineering or something is less problematic. But maybe I'm just naive to that.
I don't know. Some of the, I keep hitting the microphone. There'll be bumps in the recording all the time. But some of the students that have been most meaningful to me were not necessarily the ones scoring the highest marks all the time. I have one of the students, there are two students now, I just came to mind, two students that I would hire them any day of the week. I don't think any of them got first class in their degrees. One of them failed one of my units in his first year. Failed one of his units. And he had to repeat the year, just that unit, because we wouldn't allow him to progress to the second year. I was quite tough on him. But you know what? He hated the unit. He didn't like it. And I tried to support him as much as I could. I said, you need to do it. You need to pass. And then you can forget about it if you don't need to use it. And he managed to succeed. And then he ended up with a master's here, never failing again a year. He actually was part of the team who went to the iMake Design Challenge competition in London. So it's a competition I organize. And he was part of the best team when he was a repeating student. And another student I had, which was also a similar situation, he was struggling a bit. And at the end of the first year, he comes to me and says, how do I do to withdraw from from engineering? I want to go to economics. And I have this conversation with him, and I say, well, I think what's the problem? Oh, I don't think I like this very much. I think what I want to do is business. I said, well, you see, I think being an engineer is good, and you do an MBA and stuff like that. So you're still trying to test the waters. Then he appears in the second year. Halfway through, he goes, I want to step down. I don't like this. And he did it until the end.
and he kept repeating this process of not feeling like he didn't want to be there. But.
And for me, what is really amazing about that is that what he's demonstrating to me is that even when things look a little bit adverse and against you, and you might not be enjoying, because that's real life. I wish I was working in the aerospace industry, but I started in the rolling stock in trains. So it's like you can't really choose that. Sometimes you can't choose what you do. Is to be able to demonstrate that they can succeed even when there are barriers and challenges ahead. And he became a good student as well. And I don't know what he's doing now. The other one is in touch with us. They are coming here for a talk. So he's coming here for a talk, the other one. The first one I talked about. But it's sometimes there are students that quite surprised. Oh, I have another one. It was not very. Oh, sorry, you can then cut down all this. He was a first year student, not very strong. Second year, I had another competition in units called engineering simulation. So what I did was they had to optimize a part from a car. I'd give them to them. They need to use a computer, and there were some target specs they need to do. And he was attending all the lab work, all the CAD labs. CAD means computer aided design, or CAE, computer aided engineering labs. So using software to do simulation-based work. And he turns to me and says this to me, you think I'm the underdog, but I will win this competition.
Was it Al Pacino? It sounds like Al Pacino, the way you're saying.
And he did.
Really?
He won. And he went later on. He was my final year project student. He did a stellar job. He's the type of student who, when he wants, he's the best.
Right.
When he doesn't care, he passes. I love that. I think that's really good. If I just, okay, I have to do it, not taking joy, I don't see the value, I'll do it to the bare minimum. If I'm really enjoying it, I'm going to be the best. And he was that. Really, really good. So there you are. Another example of someone who didn't finish with first class.
That sounds like a student who knows that they're there to do things because they want to learn things they're passionate about, as opposed to someone who just wants a certificate at the end that says 70 or above it.
Yeah.
Because I often find there's a distinction. Like, it bugs me no end when students say, what do I need to do to get a good mark on this or whatever? Yeah. Or, they're so transfixed sometimes on the assessment brief that they forget to learn in the semester before. It's like, you're here to learn. You're not here to just get a a degree.
I agree. But that's if this goes on air, and if anyone watches this, or students in particular, I don't think having first class marks does necessarily make that difference. It could help, but I think it probably helps more to employers to see your extracurricular activities, your hobbies. So that when I first started writing CVs, I couldn't understand the hobbies things, and I never valued that. And now that I am actually looking to CVs, I don't want to see first class in mechanical engineering, first class in mechanical engineering. Well, who cares? I want to see, everybody has that when they are applying to, that's probably essential criteria is to have the degree. So I want to see the other stuff. What is it around that?
Who is the person?
That makes you the person for me to want to recruit you. So what's the differentiating? Because you are applying for that position, essential condition, having the degree in engineering.
Is this recruiting for the university?
Even for university, for example, yeah. I do a lot of recruitment, yes. So you need to put there things that meet the criteria, obviously, because we have a person specification. But what is it that makes you being exciting? What are you giving to the business or the university that we don't have? Which is really difficult. It's really difficult to do, but I think that's you receive a pile of 50 CVs.
How do you differentiate them?
You have to be quick.
Yeah.
So motivation letters need to be written in a certain way that highlights certain stuff, and it's not just the first class degree that's going to. Obviously, I don't recommend students to have a third class degree.
Or just don't write it on your CV. Definitely.
That's probably try a bit harder.
But as you say, it's not necessarily. It's more of a sign of overcoming adversity that is inherent in everyone's journey through education. That if you come out of it with a good grade or whatever, it's just showing that you can deal with all that adversity and still bounce back and achieve something. I suppose.
Yeah.
It's not necessarily suggesting that you're going to be the best at that job or whatever in the real world.
And what I say is, if you are shortlisted, sometimes you could even tell a story. Why didn't you get the first class? Would be a question. And the answer could be, well, because I was busy doing their stuff, and that took me time, or because I planned to have, this was my target. If again, for me, that's the quality thing. If you say to me, my target is to have a third, and if you get the third and you don't fail, I think that's a pretty good outcome, because it's probably difficult to try to get the thirds and pass at the same time. How can you control that? Isn't it?
So you'd be impressed if someone achieved to land in the correct band.
If someone would say, my target is to be in this band without failing,
and what you're
then I think, wow, this is
what you're thinking is maybe because they're optimizing the amount of effort they put into their degree versus maybe they've got a job outside, or maybe they're a carer or a parent or whatever. They've optimized to the point where they know exactly the amount of effort they need to put into their degree to come out with the third.
Yeah, for me that's probably you might disagree, or people watching might disagree. No, it's of course, it's debatable, obviously, but I think it's I think it's hard. It's probably harder to have that control of it's probably easier to try to get to 70 and then you get 40 because you thought you knew certain things that you actually don't know. So that's what will happen to me.
That's an interesting way of thinking about it.
So it's just a way. It's just a perspective.
It comes full circle back to your headlight story, doesn't it? Really, that as well.
Yeah, exactly. Yeah. So now it's probably
right. Diogo, how do you pronounce your surname? I don't want to get that wrong.
Montalvão.
Montalvão.
Good.
Yeah, and it's actually Diogo, isn't it? Diogo. Is that good?
Yes, perfect.
You didn't seem so sure when you said perfect.
Because the problem, if I say it in Portuguese, it's Diogo.
Diogo. Yeah,
it's we close the vowels.
Okay.
If it would be in Portuguese Brazilian, you'd probably say Diogo.
Right.
Might you open a bit more.
Okay.
Yeah. So it's Diogo Montalvão.
Okay. Dr. Diogo Montalvão. Thank you so much for coming and chatting with me today.
Thank you for inviting me.
I really appreciate it.
Thank you for having me.
And I can't wait to go and see your machine in action at some point.
And the cameras, you might want to use them.
Yes.
Who knows?
What cameras are they? Sorry, we're getting onto a topic again. I'm not very good at ending this thing.
So this is a system. I can say the brands, right?
Yeah, please.
So it's a system from Dantec. I actually have 3 cameras.
Yeah.
I have a very high-speed camera, which does high-speed 2D imaging, so it doesn't measure out of plane. And I have 2 low-speed cameras that do 3D, so you could see the deformation in 3D of an object.
Wow.
But you could want to film, I don't know, it's an Amtech camera. You could film, if you wanted, a bullet going through jelly, and you want to see it in slow motion.
Do you ever watch the slow-mo guys on YouTube?
Yes.
That's
what I'm saying.
Stuff. Yeah,
so this camera does that.
Wow.
You can use it to do those things as well. Why not? It's a camera. It's a camera. I use it for different stuff.
I'm gonna have to come in and steal that camera.
Yeah,
Sounds great.
I'm very happy to that. My name goes on the paper. Okay, that's the only condition. You have to cut this.
Yeah.
But that's, the camera is there. It belongs to the university in the bottom line, and if that brings me to cooperation with other groups, why not?
Wow.
But now it's there. It's actually quicker than 390,000 frames per second. You can go higher, but you decrease the resolution.
Of course, there's always a trade-off.
Yeah. Because it's
data.
lines, yeah, and so you are filming. I'm filming just a little bit of the specimen. That's why I can go that fast. It could be even quicker if I increase the resolution. It decreases the speed.
Yeah,
but you could do that type of filming, knowing that you are in that field.
That's good to know.
Maybe you have dozens of them.
No, not at all.
Now you know who has it.
I think the fastest cameras we've got are like 180 frames per second or something like that.
That's
pathetic. Yeah. It's pathetic.
I can't do anything with that.
Or maybe like 240. I don't know. We do have cameras that go like maybe to 900, but again, the resolution is so pathetically small that you're never shooting that.
If you want to have an explosion or something like that.
Yeah. No, we don't do anything. That's very specialist, really, that for what, compared to what we do.
You never know for this podcast, like the
film this whole podcast in like 300,000 frames per second or something.
You can see.
You wouldn't even see it like that, though, would you? It would look like a static image, wouldn't it?
Yeah.
That's an interesting philosophical thought as well, isn't it?
How
long would an hour-long video be?
The longest YouTube video in history, 10 years and a half.
And you'd watch it, and it would just be like watching the sunset where it doesn't seem to move at all.
Yeah, exactly.
But you know it's going down. Yeah, there's something's happening, but it's just nothing is actually happening. I find that an interesting thought as well, like the different like frequencies in life that you know, like a fly, with its reaction speeds, must be somehow living at a higher frequency than we are, or experiencing life.
Yeah, definitely.
Like perhaps because obviously, I said earlier the lights are blinking on and off 50 hertz, so there must be some animals that can see that flashing.
Possibly.
Maybe. I don't know.
Yeah, because the aliasing if you put here something spinning, you'll see some aliasing. Like on the cameras, when you film and the wheel is spinning and then starts spinning the other way around.
Yes.
The helicopter and stuff like that.
Yeah, all that sort of stuff. Yeah.
Yeah.
Anyway, we need to finish.
Thank you very much. Yeah,
Thank you.
Go. Thank you.